Well, thank you for coming to this session on in-memory technologies. My name is Sunil Agarwal. I'm a program manager with SQL Server team, and I've been working with SQL Server for last 15 years. And if you look at my gray hair, I've been working longer than that. So I've been working with databases, I can't believe myself, 34 years. Okay. So a lot of database experience. So I was responsible from a program manager perspective, this in-memory technology that came out in 2014. And then I moved to 2016, and my focus was the column store technology. And we have a session today in the afternoon about column store technology. So in this session, what we are finding that people are not adopting in-memory technology as much as we thought they would, okay? So the focus of this session is to showcase some customer success using this technology. And it is at a very high level. I'm not gonna show you the application code because that's like 400 level. I want to focus on the scenarios where you can apply this technology, all right? So if you walk away and say, this thing makes sense for me, and we can drill down. And I added my email, okay, sunila@microsoft.com. And if you have further questions how to use this technology in your environment, please reach out to me. I'm more than happy to respond. My job is to make customers happy. And if you call me, that's the first step, right? Okay. So I actually, before you guys came, I talked to some of you guys, and I'm not surprised. A lot of people do not know what this technology is, okay? So what I would do is first 20, 25 minutes, I'm gonna focus on the basics, like what this technology is, why did we build it, okay? And then we will drill down into 5 or 6 scenarios, like 2 slides per scenario, and there'll be some demo. And let me ask one question. This is a trick question. How many of you use TempDB? Everybody should. I mean, if you're using SQL Server, you are using TempDB, okay? So I can imagine 40% people respond to questions, others don't, okay? So in fact, you can use in-memory technology to replace some constructs in TempDB, okay? Very powerful concept, and I'm gonna show you that. Okay. So agenda for this one is, what is in-memory technology, and how do we achieve durability? Because a lot of people, when they think in memory, they think, what happens if SQL Server goes down? Does it go away? It does not. It is fully durable, okay? We will focus on scenarios where you should use in-memory OLTP, all right? And then I will follow that with some customer case studies, and then I'll do a recap of what we learned, okay? So what I'm gonna show you, why did we build in-memory technology, all right? So there are 2 trends that are very important. First is the business trend, okay? The business trend is that market is looking for more and more throughput at a lower latency, okay? And also, they want to reduce the cost. So you want to achieve higher throughput, lower latency at a lower cost. And a simple example, all of us experience that. When you go to any store, you charge through the credit card, right? The credit card transaction comes back very quickly, right? Imagine if that transaction was taking 1 minute or 2 minutes. I mean, it'll be not right. So people want those transactions to go quickly, right? So that is the latency aspect. If you look at how many people are doing transactions through credit card, it's just going through the roof. And the example is here, is that, you can see in the back, the whole thing? Okay, all right. So example is that you, if you look at the transactions that were done with credit card, in US, it was around 26, I think this is not working, okay. It is around 26 21 in 2009, 21 billion transactions for the year, and 26.2 for the year 2012. So it looks like went from 21 billion to 26 billion, but it is 5 more billion transactions, right? And if you go to 2015, it has become 33.8 billion. So the point I'm trying to make is the applications that we have today, they need to process a lot more transactions than they were processing before. So you need a system that can deliver a transaction at low latency while support high throughput, right? So that's the application trend we see. Now, if you look at the hardware trends, right? Hardware trend is also very interesting. Anybody knows Moore's law? Yeah, so Moore's law, basically, this is pretty mind-boggling. In 1970, Mr. Moore said that the transistor density on a chip will double every 18 months, okay? The green line that you show, see, it is going from 1970 to 2015. It's one of those predictions that holds even today. I mean, the transistor density is increasing and increasing. The CPUs are getting more and more complex. But what we are finding is that you don't get a giant CPU because now I can put like that many more transistors. What you get is a CPU with a lot more cores, okay? So you get a CPU with 64 cores, you can get with 256 cores, right? So they're putting a lot more, the core, the way I think about core is like a CPU, right? We are putting a lot more processors in the CPU, right? So what it means is that your application, SQL Server is an application for computer, right? Your application, if it needs to perform well, it needs to scale well. It needs to be able to use all the cores in the most efficient way, right? If it could not use those cores, then those processors are sitting doing nothing, right? Okay, that's one. Second interesting trend is here, which is, okay, I can see here but not here, so I'm going to do this. Okay. Second trend is this. This is the clock speed. The clock speed has plateaued around 3 gigahertz, okay? And what it means is, because when you're running a chip with a very high frequency, it generates a lot of heat. So if you go beyond this frequency, the chips will melt, okay? So that means we cannot go beyond that. Now the interesting point on this one is, if, let's say, the frequency could be increased, that means I could process, let's say frequency was 8 gigahertz. That means I can process twice as many instructions than before, right? Because I can run my clock at a higher frequency. That means without changing my application, if I run it, it will run 2 times faster because I'm running 2 times more instructions. But that cannot be done because chips are not getting any faster, right? So the question is, how do you get a better performance for your transaction when the clock speed is not changing? Any idea? What can you do? Sorry? Multiplexing that you can do in parallel. And number 2, what you could do is you can reduce the number of instructions needed to run the same transaction. If I could do that, right? If I reduce number of instructions, say 2x, that means my performance will go up by 2x. You agree with that point? Okay, so this is an important concept, so I'm going to show you that. So, and the third thing that we all know, the memory, the price of memory is going down like crazy, right? Now, you can get machine with 1 terabyte of physical memory for under $10,000, right? Those kind of things, think about, if you go 10 years back, those numbers were very different, right? I mean, you have a laptop with 16 gigabyte of physical memory, right? Things like that. But now, you have a lot more physical memory. So what we are seeing is, number 1, you have applications that require higher and higher throughput at the lower latency. And then you have this hardware that is completely different what it was 20, 30 years ago, right? Lot more cores, lot more memory, right? So the challenge is, how do you run SQL Server or any database for that matter that can leverage the amount of cores, CPUs that are available on the box, right? You want SQL Server to use all the cores all the time, right? Because that's when you get the maximum throughput. Second thing is, how do you use the memory in the most efficient way, right? And I think I'm going to talk about this point. How many of you have your transactional database under 1 terabyte? A lot of us. Most transactional databases are under 1 terabyte, right? So if I give you a box with 1 terabyte of physical memory, is your database in memory? Answer is yes, right? You can get better performance. So the question to be asked is that database using the memory in the most efficient way? Okay, is it optimized for memory? And I'm going to touch upon that point with an example. And we talked about the latency. How do you reduce the latency of a transaction? What does latency mean? I run a query, I get the results back, right? The faster I get back, happier I am, right? Now, there are two aspects. If I'm running as a single user, I get response back. That depends purely on the instructions executed, right? If I'm running with thousands of users, not only is instructions executed, but also how does it scale with everybody else running at the same time, right? Okay, so the transaction latency is the next thing. So I'm going to show you a very simple example using traditional SQL Server tables. When I say traditional SQL Server table, those are the page-based tables that we have, that most of you are using page-based tables, okay? You insert rows into pages, pages get flushed to the disk, right? That's what we're using. So I'm going to show you a very simple example, and I'm going to switch to my box number 1, and see if you can, okay, you can see it. So, okay, yes, there you go. So here, I have an application, and I'm going to use this application multiple times. So this is an application. What it is doing is, it is a ticket reservation application, which is like people are buying tickets. That means rows are getting inserted into the table, right? And it's just not one user buying the ticket. There are 80 threads that are running concurrently that are buying tickets, right? So what happens is, today, if you run with SQL Server 2012, 14, or 16, using disk-based tables, you will see the throughput will, you see that I'm getting around 6,000 transactions per second, which I think is pretty good, right? 6,000 transactions per second. But if you look at the diagnostics, which is the most interesting thing, if I look at the diagnostics, notice I'm using my CPU less than 40%. Less than 40%. And it is primarily because I'm getting a lot of blocking at the bottom. So that means if I was running my workload on a 64-core machine, it doesn't do me any good because I'm not able to use my CPU as well, right? So that is the challenge that we have with the disk-based tables, okay? It cannot scale beyond certain things. Now you can say, why it is so? Because when these technologies were designed, at that time, number of cores available in the system were like 8 cores, 16 cores, right? So they were designed for that kind of hardware. But now, as I said, you have 256 cores. How do you do that? Okay. So I'm going to go back to, so this is the problem, right? So I'm going to go back to the presentation. And so then the second question is, like I was asking you, that like most of us said, our database is under 1 terabyte, right? So they can fit in the memory, right? So your database is in memory. So the real question is your database just in memory? Answer is yes. Or is it optimized for memory? Okay. So I want to differentiate that you have an in-memory database versus it optimized for memory. And I'm going to give you a very simple example. So this is the most complex slide I will show you. So just bear with me. Okay. So this is a non-clustered index. All of us know about this index, right? Now imagine you have the whole table, whole database, all indexes in memory, all right? Now if I say to you, give me the address of an employee where employee ID is XYZ, right? If this was a common query, you will have a non-cluster index on that column, right? That's a good database design. So what do? SQL Server will say, okay, I'm going to choose this index, and is going to go to the root page and find out, okay, this is where I start. Then it has to figure out where I go next. Where I go next, right? Like that. Now, interesting thing is when it goes to a page, it just cannot read the page without any guarantees because somebody could change the page. So what they do is SQL Server takes a latch. Latch is a short duration lock on the page. It says, let me look at the page, figure out what is the next page I need to go to, right? Until then, nobody's going to change the page. Then I figure out, I release the latch, I go to the next page, right? Now, I found the record, okay? If this was not a covering index, guess what? The non-cluster indexes are built on top of cluster index, right? Then I go through the same thing, right? So let's say I went through 3 or 4 pages here, 3 or 4 pages here, right? So I went through 8 pages, and finally, I land on the page that has my employee record, right? Imagine how many instructions you did to get to the row that you wanted, right? So this is what I'm saying. Your database may be in memory, but it is not optimized. It is almost saying if I want to go to Sydney from Gold Coast, I'm going via Los Angeles. Almost like that, right? Because I could just go like that, but no, we're going to take you through Los Angeles and everything else, right? So this is a very important point. Is your database optimized for memory? And clearly this is not. Now, I'm not saying this is a bad design. This was designed at a time when the size of the database was much, much larger than the physical memory in the system, right? So you have to use pages to bring the data that is needed, right? So this design worked well, but it is not optimized for today's hardware. Is that point clear? Okay. Okay. So what SQL Server has done? This is like if you have done any presentation on in-memory OLTP, this is actually the slide they will show you. So there are 3 fundamental things we did with SQL Server 2014, and we improved it over time with 2016. So the first thing we did was we said, well, the data is going to be in memory. We require the data has to be in memory. That means I don't need pages, because pages was a construct because my database was much larger than my memory. Okay, I don't need pages. So I'm going to just throw rows into the memory, okay? Which means now if I want to read a row, I don't have to latch the page. I don't have to worry about it because I go to row directly, right? So there is no buffer pool for in-memory tables, okay? And I should not say in-memory tables, memory optimized tables, right? Because there's a distinction in memory versus memory optimized. Second thing we did, remember I talked about the clock frequency stuck at 4 gigahertz. What do I do? What do I do? So this is a magic. I consider it some magic. So what SQL Server team did in collaboration with Microsoft Research, all of us have used stored procedures, right? And stored procedures get compiled through Optimizer. And you know what you get? If you look at the query plan, it says, suppose it was a simple join with 2 tables, join operator, scan operator, right? Those 2 scan operators are feeding the join, right? So it is at that level, and SQL Server executes the query at that level. It is interpreted, okay? What we do with memory optimized tables, we take that plan, and listen to this, we transform it into a C program. Okay, I can show you the code. It looks pretty ugly, okay? It gets transformed to a C program. And then we go through a C compiler and generate a DLL out of that, okay? By doing that, the number of instructions needed to execute the query is much, much lower. Okay, now, even though I'm running at 4 gigahertz, I can run that guy much, much faster. In fact, what we found was that number of instructions got reduced so much in the best case. This is the best case. We needed 50x less instructions. That means I could run the query in the ideal case, okay? Ideal case, 50 times faster on the same CPU, okay? Not only because of this guy, but also because of this guy, because now I can go to Sydney nonstop. I don't have to go to Los Angeles. You see what I'm saying? That is also taking instructions. So we took instructions away. So the key point I'm making is we said we will reduce the instructions, and we did that way. Okay. The third thing, what about the course, right? We said we will do optimistic locking. And let me give you an example what is optimistic locking. So let's say you come on Sunday morning, right? I mean, and you're the only person on the database on Sunday morning. Let's just say that it is possible. And you are modifying million rows, okay? Could you not tell SQL Server, I'm the only person today, just don't take locks because nobody's gonna bother me, right? But SQL Server is not like that. He says, I don't trust you. I'm gonna take the lock because I'm a pessimistic locking, okay? So I take the lock and release the lock. So taking a lock takes 100 instructions. Releasing the lock takes similar instructions. It takes memory, right? It takes resources. So what we have done is, we said we will do optimistic locking. So we assume nobody's there. It's Sunday morning every day. We assume there's nobody locking. Now the question comes, what happens if I'm modifying a row and you are modifying the row, right? Now imagine this, right? You and I have bank accounts. You don't go and modify my account. I don't go and modify your account, right? It may happen that my account and your account may be on the same page, right? But we are not really modifying each other's rows, right? In a transactional system, I'll put some number, 95% plus changes, they're not conflicting. They're not conflicting on the row because they are changing different rows. They were conflicting because of the page, okay? So what happens is taking no lock just works fine. And we have a complex way to figure out before the transaction commits, has anybody changed the row that I saw? If it has changed, then we abort that transaction. But that abort will happen, I said 95% times nobody's changing, right? So abort happens once in a while, okay? So that is the optimistic locking. The beauty of this one is now you can scale well, okay? You can scale well. So let me show you a couple of things. Remember this, we talked about this memory, in-memory versus memory optimized. So what we do now is we have a new index, for example, which we call hash index. I want to find the row employee ID XYZ. I hash on the name, right? And I find the row. Now, isn't this much, much faster than going through 9 pages, latching, unlatching, searching, on and on, right? So this is what I call optimized for memory. It is in memory, but it is optimized as well, okay? This is what SQL Server in-memory OLTP offers you. No locking, but it gives you full consistency. You can run serializable. You can run repeatable read commit. You can run all those things, but no locking, okay? So I'm gonna show you the magic, how this changes the ball game, okay? I'm gonna go here, okay? And what I do is, I go to my ticket reservation database right here, and I'm gonna drop this table, okay? This is my old disk-based table. I'm gonna drop it. And then I'm gonna replace this table by a memory optimized table. So notice, it is saying memory optimize on. It is exactly the same table. And durability is schema and data. What it means is this table is durable. If you insert the row transaction says I'm committed, you rest assured the transaction is committed. You can shut down, you can do whatever not, database come back, right? Okay. So I just changed this table. This is the easiest example, okay? I just changed that. Did I run this guy or not? Maybe I did not. Okay, I ran it, okay? Now, I will run the same application with no changes, okay? Just run the same application with no changes, okay? All right, so I'm gonna run it here. And what you will see is that suddenly, notice I got almost 100% CPU and I got 3 times better performance. 3 times better performance, right? And it is primarily because I removed the latching locking. There was nothing locking latching, right? So that's the promise of this technology. And this is just a demo. We have many customers who have just marked the table as memory optimized table, and they got rid of this kind of bottleneck. The best case that I've seen, the best case I've seen, 2 weeks of investment, and their application became pretty insane. And I'm going to show you that example, all right? So you see that why this is happening, right? Okay. Where is 5 here? All right. So what we have found is, what is not coming? I was not using my glasses, so I press 6 instead of 5. Okay, so what we found is that with the in-memory technology, you can get up to 30 times improvement. I was showing you 3x. This is on my laptop, which is 3 years old, okay? On high-end servers, customers have been able to get up to 30x. In fact, there was one customer who got 40x, okay? So this is real stuff, okay? Okay. Typical gain that we have seen, 2x, 10x. And if you are looking for some sort of a high-level benchmark, because we do a lot of testing inside Microsoft SQL Server testing, on a 4-socket machine, socket could have multiple cores, right? On a 4-socket machine, we could ingest 10 million rows per second with this in-memory technology. We can generate 1 gigabyte log per second. We are generating so much transactional throughput. It is important. Remember I was talking about the credit card application, high throughput? We can handle the throughput. Low latency, because we reduce the number of instructions significantly, right? On the same hardware. These 30x I'm talking about, it's not somebody bought a new machine. They just said, I'm gonna just convert it and on the same machine, because most people just cannot buy a new machine because it has to depend on the cycle, right? 3 years kind of stuff, right? So we also created some sort of a workload like order processing system. We ran 360K transactions per second. It's a huge number with this technology. Now this is a Bevan party. This was a first company that actually went on production in this one. And this is what they did. I'm going to talk about with a pictorial. This is the online betting company, right? So what they had was every customer of theirs is creating a session, looking at what bets are possible. These are bets on the sports, okay? So for example, soccer is something that I don't know much about, but for example, like penalty kick is going to happen, and this guy's going to hit the penalty kick. You can place a bet. Will that penalty make it or not make it? Bevan allows that kind of betting, okay? So they needed something that can scale well and can handle a lot of traffic, okay? Before they used in-memory technology, they had 18 servers scaled out, because when you log in through web application, it will go to one of those 18 servers, okay? 18 were scaled out because they needed to do that to handle the traffic. When they went to in-memory technology, they moved from 18 to 1 because there was no blocking. One server was able to deliver the load that they were distributing over 18 servers, okay? Yeah.
Numbers, do we have numbers on how many of them got really aborted, like the transactions, how many of them?
Right. So the question is, remember we're talking about optimistic locking, and the way it happens is when I commit my transaction, SQL Server will check, has anybody modified the row that you changed or looked at, right? First of all, that's a rare event. If it happens, then it will abort your transaction, just like you have a deadlock detection. It means something. It means if your application was working well before, because it would have been blocked, but now it will be aborting. So you have to put the logic in the code to say, if my transaction aborts, I need to retry. So that kind of change you have to make. Application has to make that change. Now the question is, how many times this happens? It depends on the application, right? Okay. So I got half an hour on this one. So here is what you do. Like you say, I'm going to create a table. Look at this one, right? Sorry, I think I'm not missing that. Okay. What happened here? Okay, yeah, I'm here. So notice that it is just saying, table, the column names are very similar. And it's saying the durability is schema and data. That is a default. And interestingly, you can say the table is non-durable also. You can say the schema, the durability is schema only. You know when that can be useful? Why do you want table not durable? Any ETL, like if I'm doing a staging of my data, right? I load data from a external file into a staging table. Today, people use a table in the temporary database, right? Because they want it temporary. Now, you can say, I'm going to have memory optimized table, schema only. So that means no logging, no writing to the disk. You can do staging much, much faster. And no locking. You can load data into staging table in parallel. Okay. All right, the DDL, memory optimized, what happened? I think I'm messing it up. Okay, procedure. Remember I was talking about converting into the C program? That's a native. You say this is a stored procedure, and it is native compiled. The important thing to note is your existing stored procedure will work without change on the memory optimized table. Remember in the ticket reservation database, I just changed my table from disk-based to memory optimized table. I did not change my code. I did not, right? So, but you have two ways to execute queries on the memory optimized table. The old way, which is going to be slower because it is interpreted, and the new way through native, which is going to convert into the C program and the DLL. You see what I'm saying? Okay, so most customers that we talk to, we say, you know what? Before you churn the ocean, just figure out which tables are important for your workload, which are performance critical. Just move those tables to in-memory and continue to use your old stored procedures and see you got some benefit or not, right? So that's what we say to our people. Sorry? Indexes. Right. Okay, so let me touch upon index point. So, you know, you have only B-tree indexes on your traditional tables, right? So the index is called the range index for memory optimized table. So what we say to our customers is when you are migrating from disk-based table to memory optimized table, just convert those B-tree indexes to range indexes. Similar functionality, non-blocking functionality. Now it is possible with the memory optimized table, things are running so much faster, you may not need all the indexes, you may drop some indexes, that's one. Some indexes are only used for equality predicate. Suppose I'm saying, give me an employee ID XYZ. For that, you know hash index I was showing you? Hash index is the most efficient way. So there are two indexes available, two types. Range index, which is like a B-tree index, and the hash index, right? So that's the guideline. You can create functions. I'm just going to go through faster. The key point is you can create tables, functions, table types using memory optimized tables, okay? Now let me talk about durability. This is actually important, and then I'm going to show you a demo to you. So unlike commonly people believe in memory means system goes down, my transactions are gone, it is not the case, fully durable, right? This is the default. If you say create table, memory optimized table, you don't say durability option, it is durable. That's what you want, right? Now the second option is delayed durability, okay? What it means is, you know, when you commit a transaction, let's say I went to my ATM, I deposited $100, right? So when my card comes back to me, it better ensure that my transaction was committed, right? If it was not committed and I went home and told my wife that I deposited $100 and transaction did not commit, who knows what happens, right? Okay. Delayed durability, right? It says you can relax that requirement. We will say transaction committed, but we will not guarantee that it made it to the disk. That means if SQL Server goes down, you lose that transaction, okay? Now, why it is so important, okay? I'm not saying you will use this mode of transaction for your database, for your banking application. You will not, right? But there are situations. So for example, if I'm collecting the telemetry data from a lot of sensors, like data is coming, right? Generating a lot of logs. Now, if I lose 5 minutes of my sensor data, it's not a big deal. You agree? It's not your banking transaction, right? So there are workloads where you can say, I'm going to run this guy under delayed durability. What it means is now your transaction throughput can be higher. It's not really waiting for the log to get flushed, right? Now, this capability is available not only for memory optimized tables, it is also available for disk-based tables. All right. Any questions on this? Okay. And we already talked about the non-durable tables, which is best suited for staging table for ETL. And remember I was talking about B1 example where customers are logging in. They said if system goes down, the worst case is people will lose their session, right? It's not they will lose their transaction. They will just lose their session. They said we will do it under non-durable tables. So that's what they have done. So there are staging example like in an ETL example, or you can do this way. All right. So now let me just show you in the demo way. Yes, sir. What is the secondary thing?
So you've got your, from what I gather, you've got your in-memory, talking about delay durability, right? So you have your data that's sitting in memory, and every couple of milliseconds or seconds it's getting committed to disk as well. Can you, from Management Studio or from whatever, can you only access the in-memory layer, or can you go specifically and access the disk layer?
Right. So the question is, if I have delayed durability, how do I access my data? I mean, we all know that the data in SQL Server, whether it is memory optimized tables or disk-based tables, it is accessed from memory, right? Because we will read the data from the memory, from the disk to the memory, right? Okay. If SQL Server did not go down, let's assume that, the delayed durability, you will not lose any data, right? Because everything is either in memory or on disk, right? Okay. So what is delayed durability saying? When I say commit my transaction, SQL Server makes sure the transaction log for that transaction got flushed and got secured on the disk before it says, okay. It's just that delayed durability says, do not wait for that. That's all it is. Okay.
Is there a massive bottleneck on the log file then?
Sorry?
Is there a massive bottleneck on the log file?
Log file is sequential, right? The logs are being written sequential, but the problem is if there are like, you imagine this, if you're running on 256 core machine, everybody is writing the log records, right? So there is a lot of contention on the log buffer, and then we have to make sure log buffer gets flushed, right? Because until it's flushed, I can't say transaction committed. So it just takes that equation away. Yeah, it just makes it much faster. Okay. Now I'm going to show you a quick demo, and then I'm going to go into the scenarios, right? It's 12:08, 40 minutes. Yeah, so I think we will be able to do that, all right? So I'm going to do this, right? So notice I got 3x performance. And now what I'm going to do is I go here and I change the durability, right? So what I'm saying to my database is delayed durable is good, okay? So I'm just going to do that. I did this. And now if I run my workload, you will see, now what happened? You see there is some increase, right? Right? And it is because now my transaction is not waiting for the transaction log to get flushed, right? So I got a little bit more throughput. Again, I'm not saying you do that for your banking transactions. You're doing for telemetry data, right? You see that point, right? So the next thing that I will do is I'm going to change my table from durable to non-durable, okay? I'm going to drop this table, and I'm going to create this table, same schema, except I will say it is schema only, right? So let me just do that, okay? Right? And if I go here and I run my workload, you will see it is a little bit more high, right? I mean, this is fluctuating because my IO device is pretty bad. But what I'm saying is, it is much, much better, right? You see those peaks that I'm getting, higher peak? The last thing that I will do, remember I was talking about this native stored procedure. I go here, and I convert my stored procedure to native. I'm going to drop the stored procedure. I dropped it, and I'm going to create this stored procedure. Notice I'm saying, somewhere I should say native, right? I'm saying native. So I'm replacing my old stored procedure with the native stored procedure, okay? And I'm going to execute that. Okay, now if I run my workload, you see that? So what I'm trying to show to you is that starting from what you have today, you can get this kind of a motion depending on your requirement for the workload, right? Okay. This is all in memory because I'm using.
The compilation piece, the stored procedure compilation, will that help for non-in-memory databases?
Which?
Nothing there that says that it's dependent on it being in memory. You've compiled all your stored procedures now in native, and that without any in-memory use.
So, sorry, I'm not able to go slow on me because.
Without actually doing any in-memory optimization, could you take your stored procedures and compile them?
Right. Okay. Yeah. Right. So the question is, it's a great point, right? We take a T-SQL stored procedure and run it through this transformation to C program. Interestingly, it is orthogonal to memory optimized tables. It is, in fact. But we did not do that optimization for traditional tables. And that is something that we were thinking about. It's just that we wanted to nail this scenario well and come to that, exactly that. Yeah. So I hope this sort of painted the picture what all is possible with the memory optimized tables, right? So now I want to go through some customer scenarios that have been successful with memory optimized technology. All right.
So in terms of the question, in your stored procedure, would all your tables that you referenced in that stored procedure have to be memory optimized for you to change your
Right.
stored procedure?
Right. So here's the interesting point. The traditional stored procedure, it can access memory optimized tables and disk-based tables without any problem. Okay. So for example, if I had a stored procedure that was running with 3 tables, one table was performance critical, I can just move that to memory optimized to stay where they are. For native stored procedure, I think going back to the point that you're making, we require that all tables referenced in that procedure must be memory optimized. And once we solve that problem, then we will be home free. Yeah, okay. All right. So we talked about that case studies. Okay. So I'm going to have a very high level. Oh, it's not there yet. Okay, 5. All right. So what I'm going to show you is when to use in-memory table, right? You should have a general idea. First is when you want to increase transaction throughput. I hope that point has been nailed here, right? Second one is data ingestion rate. You can ingest data at a much, much faster pace. I can show you how. Because what happens is when you are ingesting data from outside, loading data into a staging table, you don't load data from a single file. You have multiple files and loading the data. And what happens is if multiple guys are inserting into the same table, they get into blocking, locking, right? With memory optimized tables, that problem goes away. You can do ingestion at a very different deal, right? Okay. Reduce latency. I showed you with the memory optimized tables, native stored procedures, you can run the same thing much, much faster than before, right? Okay. Latency spikes. What we found, I mean, I'm sure all of us have experienced that. Things are working fine in my test environment. But when I go to production, things are fluctuating because users are coming and going. There is a lot more fluctuation, right? There are spikes. With a memory optimized table, expectation is the spike goes away because you took one of the key issues that lead to spike, that is the blocking, locking. right? Okay. Transient data scenario, like a staging table we talked about, session state, right? Reduce pressure on TempDB, which I'm going to touch upon. Do not use, so it is not a magic thing that works for everything. It is not, right? If you are running analytics, analytic queries are running on tens of millions of rows, okay? In-memory OLTP technology is not for analytics. For that, use column store index, okay? And that is something I'm co-presenting with Sudarshan this afternoon. So that's the technology, right? So of course, use the right technology for the right problem, right? So that's that. Second thing is, if your application is very chatty. Now this is the important point. Remember, all this optimization that we have done is inside SQL engine, okay? If your application for a given transaction does user-based input, right? Many, many chats with the user, the majority of the latency in the transaction is going over the wire, waiting for the user input. You see what I'm saying? So then, for that transaction, you will not get any benefit because we are only speeding up what is executing inside SQL Server, okay? So chatty application, no, 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 right? Low transaction volume. I mean, if you're running 10 transactions a minute, nobody's running 10. But suppose you're running, you're happy, right? I mean, everything is working fine. Why run around? The problem comes when you are running a very high transaction throughput, right? Now, on this, let me make one quick point, which is actually very important. How many of you know about 2016 SP1? Okay. You know, the biggest announcement we did for SP1 was all enterprise features are now available on standard and express, okay? In-memory technology was not available on standard edition, but now it is available, right? Now, why did we do that? Okay. Now, imagine this, right? You are writing a ticket reservation application for your high school, right? You are running like 20 transactions per hour. I mean, if you're lucky, right? I mean, so you say, okay, I'm going to use standard edition disk-based tables because I don't need high-end features, right? And now, suppose your application became so popular that who's the famous rock star? Lady Gaga is, right? Their business manager calls you and says, you know what? We want to use your application for Lady Gaga's concert. And guess what? It will fall apart because it is not going to scale, right? So that's the problem, right? So what we said was, if we make this technology available in the standard edition, then you will use in-memory technology for ticket reservation because you want to run that faster even for your high school. And now, if Lady Gaga calls you, you can say, okay, I'm going to move from standard to enterprise, but I do not change my application. It continues to use in-memory technology, right? So that's the reason. So this is all available now for everybody. So one of the reasons, hope we have is that people will start using these technologies because the barrier to use this technology is very, very low now. Yeah? Okay. So low transaction volume, of course not. Of course, the memory optimized table require those tables must live in memory all the time, right? If you do not have enough memory, then of course, tough luck, right? So that's the thing, okay? Any questions? And then I'm going to go through these scenarios, and let me just see how much time I got. 12:20. I'm just doing. We started 11:30, 12:20, so we got 25 minutes, right? Okay. Yes, sir.
Just a quick question. If you had re-enabled the consistency of the data and still compiled your stored procedure, does that speed bump on a compiled stored procedure require you to reduce the robustness of your data or not? Or do you still get that speed bump? In your demos, you had the storage was not consistent, durable, and then you said not durable and you got a speed bump, and then you said you compiled your stored procedures native and you got another speed bump.
Right. So
You've still got durable data, you still get a really good speed bump with a native compiled.
that's right. That's right. Yeah, yeah, yeah. So the question is, native stored procedure is orthogonal. The speed up because of native stored procedures are orthogonal, whether the table was durable or non-durable, right? Yeah. Yes, sir. One question, then I think, yeah.
Yeah, with your stored procedures, they have to be specific types. They can't be like parameterized or anything like that.
No, no, they can be parameterized. I just use a very simple stored procedure. Yeah, yeah, yeah. We are pretty much support. Our goal is the goal. We have not achieved that. That you should be just able to take this thing, drop it here, and it works. Yeah, we're not there yet. Okay.
What about queries that developers do direct from their code, like EDM models and things like that? Are they impacted by tables or databases that go in memory? So using entity framework, for example, or LibQ queries?
So,
Not using stored procedures.
right, right. So the thing is, in the entity framework, I think the queries are generated, right? Right. So they are ad hoc queries, right? They're not stored procedures. Right. So they will be able to, they cannot use native stored procedure, right?
Well, we've got a combination of stored procedures that I write, and then they do direct queries to insert or inject data.
Yeah, yeah. That should benefit. That should benefit. Yeah, yeah. That should be fine.
But do you get performance improvements to their queries as well?
So you will get performance improvement if the table that they are touching is memory optimized table. Absolutely. Absolutely. Okay. So I'm going to go through some scenarios. I don't think I'll be able to go all of them, but let me just go through as many as possible. I'm definitely going to spend some time on TempDB because I'm really excited about that point, right? So scenarios are high OLTP throughput, low latency, ETL, session state, shock absorber, TempDB replacement, and IoT, which is the Internet of Things, those kind of scenarios. All those things, we have customers for each of those scenarios, okay? Now, high throughput by removing lock and latch contention, right? The first example that I have, like a ticket reservation example, is ideal example for that, right? So you see that. As I said, we have these a order processing workload. The reason I put the link there, in the GitHub, if you go, this application is there using a memory optimized table. You can download and play with it. And we got this much 360 transactions, 360K transactions per second with memory optimized table, right? So this is one of those ideal situations for memory optimized table, right? We are able to achieve the low latency. Think of this, right? 0.5 milliseconds. You can achieve that in a client-server application. It's pretty mind-boggling, right? Native compilation, we talked about, reduces CPU cycles in a pretty significant way, right? So question is, this is most people ask, okay, I have database with 1,000 tables. Which table should I convert to memory optimized table? Which one, right? It's a tough question. So you cannot just choose one table to say this is it. You need to figure out, is that table performance critical or not, right? If it is not performance critical, no worries, right? So we provide a tool as part of SSMS. You need to run your workload. It will come up with a first order approximation. Don't think this is God's word. First order approximation, okay? And you figure it out, right? So that's how we do it. All right. ETL. ETL scenario we talked about, but I think it's important. When people are thinking ETL, well, my data comes in the night and whatever not, and I have whole night to load the data. That was 10 years ago, right? People are loading data at a very high rate. Needs to land to the data warehouse because you want to analyze what's going on, right? So the key point is, how do I reduce my ETL time? Because my window is shrinking and shrinking and shrinking, and my data is growing and growing and growing, right? It's like you are squeezed to the last minute, right? What do? So you have your operational database. You're getting the data. What you do now is you move data through SSIS package or BCP or the bulk inserts or whatever, right? You load data into schema-only tables. The key benefit, you can load the data without any logging, whatever not, right? You can load it at much higher throughput. And when people load the data, they need to clean it up, right? They need to do some transformations. You can do those transformations. I'm talking about the ideal case, right? Ideal case, native transformations. That means you can load the data and transform the data at a much faster rate than before, right? And then, if in the ideal world, you will move this data into the column store for faster analytics, right? Yes, sir.
In a scenario here with staging, would you be using more the native props or more only native props instead of the tool like SSIS? Would you be using SSIS more just to pull store props?
Right. So you will be using SSIS. The question is, native. See, the thing is, don't think of native stored procedures. Think of whatever logic that you were using to transformation. Keep it the way it is. Okay. What memory optimized table gives you is a way to load the data much faster because of no locking and blocking, right? And also because it is schema only. Now, if SSIS package load the data, and then you're doing transformation inside the database, right? Then native could be helpful if you need to, right? Okay. So this scenario is clear, right? People say, well, in-memory OLTP is for transactional workload, and I have a data warehouse. Well, the point is, you can still use it, right? For the ETL, which is a very significant part. Okay, the session state caching. So this is, I'm going to fast on this one. So this was like an ASP.NET session state. And this B1 application, this is the example I was giving. They had, these web servers, they had like a lot of SQL servers. And what they did was, they just migrated to in-memory. And so notice, see what happened. From all these SQL servers, they just landed to the one SQL server, right? And 1 million requests per second. I mean, this is like insane. Their requirement is approximately 200,000 requests per second. That's their current requirement. But they are so happy, they say, in case my business grows, which I hope it does, right, they are sitting pretty. I mean, they can handle 2 million, right? So see.
How does non-durable work with mirroring or something like that?
Okay, so the question is, non-durable, does it work with mirroring or always on? Answer is no, and the fundamental point is, mirroring or always on is based on transaction log, right? Non-durable, when you create a non-durable table, that creation is logged. So here's an actually interesting point. In TempDB, if I create table T1, okay, and I restart my SQL server, T1 will be gone. But non-durable table, at least the schema is durable. When you restart, the table is there with 0 rows. Okay. All right. Now the shock absorber. So let me talk about this example. So this actually is a company, Beth Israel. This is some healthcare company in Israel. And they want to identify security threats. So somebody wants to break into their system. They are going and logging the system. And what they do is, all the things that are coming out of domain controller here, they are capturing those events. And they are doing some analytics on it to see, is this pattern kosher or not? If the pattern is not kosher, that means something fishy is going on. I need to figure that out, right? Okay. Now this thing works well for them. It works well for them, except what happens is, if there is burst of activity, like suddenly some hacker comes in and he has 1,000 machines, he is running through it. Disk-based table, I would not use the word choke, but disk-based table will slow down because suddenly number of events being generated is exponential because somebody is trying to break into my system. Okay, so I will not be able to process events as fast as I would like to. And then what they do is they move the data hourly into disk-based tables for reporting, right? They want to detect the anomalies in the system. This transformation does a lot of complex things. They have a lot of indexes on this table because they're running all these kind of queries, right? So they were not happy with 1 hour delay in their analytics because bad guys can come and go before you blink your eye, right? So this was the challenge they had in the system, okay? So what we did was, we said, okay, let's do in-memory. Now think about this, right? In-memory, we move to memory optimized table. I go back so that we don't lose it. Disk-based tables, right? I go in-memory. So with the in-memory table, I mean, I hope I have convinced you that spikes is not a big deal, right? I can handle it. So spikes were happening. And then what they did was they moved to column store. Previously, they were not using column store. So when they used column store, they dropped some of those indexes which they needed. In fact, they dropped some of the aggregates that they were going to do because column store can do aggregates very, very fast. So by doing this and this, they are able to run the query in 10 to 20 seconds, unlike 75 seconds before. And, okay, I'm just going through, a little bit rushing on this one. So what you see is that they got 4 to 6 times better performance. And now they can run this migration every 5 minutes because they have much less blocking, locking. They can do that much, much quicker. Right. So this is a scenario that is live in production with memory optimized technology in combination with column store. Right. Yes, sir.
How do you size the table if you're getting a huge influx and not wild memory?
Right. So the question really is, like when you get huge influx of rows, like events, it will blow up the table. There's no doubt about that, right? So in their example, like yesterday's data is not interesting, right? So they clean up the data every day. So they have to provision the memory for the max. Absolutely right. Yeah. So I think this is actually a very important point. Unlike traditional tables, where you don't have to worry as much about how big the table can grow as long as you have disk-based storage. With SQL Server 2016 memory optimized table, you need to make sure you have enough memory. So what happens is, if my memory is not there, what do I do? SQL Server with memory optimized table will just hit a roadblock. It's almost like transaction log, there is no space left, that kind of stuff, right? So what we have done is, and hear this out, we support SQL Server with 24 terabyte. SQL Server can have 24 terabyte of physical memory, okay? I'm not saying 24 terabyte will be cheap. I'm not saying that. But the point is, you should not run out of memory. I mean, you can add memory because Beth Israel will say, I would rather add memory than somebody hack into my system. Yeah, okay.
So what happens when it stop the whole
That's right.
process?
Right. So the thing is, think of this, right? If I am out of memory, I cannot insert a row because I can't page it out, unlike disk-based tables. It's like my transaction log is full. Now you will say, why could I not page out, right? This is something we have been struggling because we want to solve that problem. Because even if you could add memory, it's not you go to your 7-Eleven and buy the memory, right? I mean, it takes time. Yeah. So the thing is, could we not page it out? People say for short duration, I can handle lower throughput, but don't kill my workload, right? So we are working on that aspect. Yeah.
Can you restrict it per table, like memory allocation?
You cannot. It is per database.
Okay.
So what we say is, so 12:33. I have only 10 minutes left, right? So let me rush through because I want to show one more thing to you, right? So this is another example. This was a company called EdgeNet. What they are doing is they provide this update of inventory into some disk-based table, right? And in stores like, I don't know the stores in Australia, but for example, you have Home Depot or a lot of stores which are carrying inventory. And so you call the store, I want to buy this thing. Based on this information, they say, I have in the store. You go there, guess what? It is not there because inventory was not updated in time, right? Okay. So they were updating this data every, I think they were updating twice a day because it was taking them 40 minutes to update because it was loaded in parallel. And so they were saying, well, while this is being loaded, People who are querying it can't query it, right? Because it's getting reader-writer blocking. So I'm going to update only twice a day. And to solve the problem of the readers, what they did was they added a mid-tier cache, right? They said, I'm just going to cache it here so that queries are fine. But the problem was the data that they were seeing here was updated twice a day, right? You don't want your customer to come to your store and find the operation, like the stuff was not there. So what they did was they just moved to memory optimized table. They just moved to memory optimized table and they removed the mid-tier caching because now there is no blocking. I can just do reader writer, no issues. And because it is updated much faster, right? It takes like 4 minutes. So they are doing a lot frequent updates. So they are actually pretty happy with the system because now they're not stuck updating twice a day. They can do, yeah. So that's that. Okay, so I got to my memory of temporary database. So I'm just going to show you that example. So this actually is a very important thing because a lot of times people say, you know what, I cannot change my application, right? Which is true. But this, I hope, is a compelling option. How many of you use pound tables in your stored procedures? A lot of us use, right? Okay. You know, the problem with the pound table is if you have a hot stored procedure, which is called by thousands of users at the same time, it can add a lot of contention in TempDB because each time you access pound table, it is created. It is created in the stored procedure, assuming it is in the context of a stored. It is created, populated, destroyed. We do some caching. I'm not saying we do not do caching. We do some tricks in the background, but it is a significant bottleneck. Okay? The bottlenecks are, you know, that you have these, I hope you know these terms, the PFS and the GAM, these are the allocation contention because whenever you are doing pound tables, even though they are temporary, we need to make sure there is storage for them because if pound table increases in size and there is no memory, it goes to the disk, right? So there is a storage aspect to it. So what we have done is we say you can replace your pound table with a memory optimized, not table, variable. I'm just going to show you that example, okay? And I think that may be the last thing I could show you today, and then I'm going to wrap this up. Okay. All right. So it is, I was actually hoping to create a demo which is like multi-user coming, but I could not create in time. So just bear with me on this one. Okay. So what I have is, I go to this database, use ticket reservation, right? And I create a stored procedure. See, this is a stored procedure, okay, declared. And then I'm creating a pound table, right? And then I'm inserting 20 rows into this table. And then I'm exiting. I'm not doing anything useful. This is just a demo. So I create a pound table, right? And I can replace this pound table by a memory optimized table variable. So I'm creating a table type, right? Same columns like before, and memory optimized on. So what I've done is I've created a table type variable of memory optimized flavor, right? And then I'm going to create my stored procedure, foo in memory, okay? And declare, instead of declaring the pound table, I'm declaring a variable of type I just created. And then I'm inserting 20 rows and I'm done, right? Now the table variable is non-durable. There is no storage involved with that at all. All right, so now what I'm going to do, I'm going to run set no count on. I'm going to run 10,000 times that stored procedure. I'm running single threaded, right? So it's not going to see concurrency bottlenecks because if you run multi-threaded, you will see concurrency bottleneck, which goes away with memory optimized table. So this is not the best case for the scenario I'm talking about. This, I can tell you what happened this morning. It took like 10 seconds. So it should finish. So imagine this 10,000 times is creating the table, dropping the table, right? And it finished, like around 9 seconds, right? I'm going to do the same thing with this guy. And it should finish 5 seconds or something, right? So the thing to note is, I'm holding my breath now. Oh, it did, right? Yeah. So you see the point, right? The same thing, I'm able to get better performance. And notice, this is just a reduction in the code path, right? There is no concurrency involved. Same guy was running the same thing, right? You know why the code path? When you do pound table with 2 columns, you know what SQL Server does in the background? It creates the table in the system catalog of temporary database. It adds 2 columns. And if the table has to be dropped, it does the reverse, right? So there's a lot of code path. And that's why we are able to run 3 times faster, right? And if you throw in the allocation bottlenecks and those DDL bottlenecks, it'll be much, right? So this is a pretty compelling scenario to think about. All right. So I have one more scenario, which is IoT scenario, but I'm going to skip that guy. Essentially, this was, again, consuming a lot of data and making it worthwhile. Okay. Now, recap. Durability options for low latency, right? You have these durable table, non-durable table, delayed durability, stuff like that. And we talked about when to consider in-memory table, right? High throughput, low latency, shock absorber, all kinds of stuff. It's very compelling. And there are many, many scenarios we talked about, right? Okay. So I'm rushing through this slide, and there are resources. The slides are available for download. And please do the session evaluation, because we just hopefully improve with that. With that, you're all set to go for lunch, and thanks for coming. Hope you liked it. Yeah.